Hello guys, I'm Dr. Om Prakash Tanwar. Today I am going to discuss about the uses and mechanism of action and its application in medicinal chemistry or organic chemistry about the reaction that is known as Curtius reaction or Curtius rearrangement. So let us first discuss about how can we make this compound like 4-amino 2,4-di-2,5-dichloropyridine. So if we want to make 4-aminopyridines or like this compound, how can we make it? So first of all, if we want to make an amino group, we can see it as nitro group, which can be converted to amino after reduction. So is it possible to prepare a 4-aminopyridine or 4-nitropyridine directly? I think that's not possible, because nitration of pyridine or substituted pyridine will give you meta directed or meta nitropyridines. So this reaction might not possible. If we nitrate this compound, then we'll get nitro here. Instead of nitro here, we'll get nitro here, and if we reduce it, we'll get 3-amino 2,5-dichloropyridine. So that's not a good idea. So we can do something else. Yes, there is another possibility that we can convert this 2,5-dichloropyridine to pyridine N oxide. Then if we do nitration, then nitration exclusively moves to para position or fourth position. This is the shift in the reactivity. Because of this N oxides directs the electrophilic substitution to this position. So this will give you only 4 substituted pyridine or 4 nitropyridines, or in this case 2,5-dichloro 4-nitropyridine. Then reduction will give you this product. But there is a problem with this reaction. What is the problem? That you have to use peroxides and N oxides you have to produce, then do nitration, that is again fuming reaction, then do reduction. So this is 3-step procedure and the overall yield is 75%. So can we do it another way? Yes, there is another possibility that you can use Curtius reaction in here. So there is a reagent that is known as DPPA, diphenyl phosphoryl azide, which gives protected amine or direct amine if we use carboxylic acid as an starting material. This is again a cheap material. This is a latent amino group, or you can say precursor of amine. So if you use these conditions, you will get a carbamate here, because we are using T-butanol as a solvent or nucleophile. We'll discuss it afterwards. And then you can deprotect it to get amine, and this has got overall yield of 94%. So this is very famous reaction, and we'll discuss today its usefulness. So what is this reaction actually? So Curtius reaction or Curtius rearrangement or Curtius degradation is a thermal decomposition of an acyl azide to yield isocyanate by loss of N2. We'll discuss this reaction. So this reaction is Curtius reaction. So azide gets converted to isocyanate with the loss of nitrogen gas, and this is very favorable reaction because nitrogen is very stable. One product is stable, then your reaction will move forward. This is favorable reaction, and if you treat it with some of the nucleophiles, then you will get the product accordingly. So here in this case, water is a nucleophile, so you get primary amine and CO2 as a gas. Again, this is a gas, So CO2 is quite stable. So this again reaction will proceed further. If the nucleophile is an alcohol, the resulting product is carbamate, and if the nucleophile is amine, then urea product is obtained. How? Suppose you have got isocyanate and you treat it with alcohol, then you will get a carbamate like this. R belongs to that type of alcohol. Like if you have ethyl here, ethyl alcohol, so you will get ethyl here. If you have propyl, you will get propyl here. If you have butyl, tertiary butyl, you will get Bock protection. Like this is that will be, if it is like this, tertiary butyl, so this will become a Bock group. This will become a Bock group. And if you instead of alcohol, if you use amines, so you will get urea. This R will be this R dash. So according to your choice, you can get different products using this Curtius rearrangement reaction. So next you will discuss that R group can be alkyl, cyclohexyl, aryl, or heterocyclic or unsaturated group. So most functional groups do not interfere in this reaction. So what is the history? Actually, this reaction was discovered by Theodore Curtius. His full name is Julius Wilhelm Theodore Curtius in around 1890s. So he discovered other reagents like hydrozoic acid, hydrazine hydrate. You might use this reagent in many functional group detections and some in your undergraduate programs, practicals. And also hydrozoic acid, which is used in Schmidt reaction. That is a similar reaction like Curtius. So Curtius reaction is closely related to Lawson and Hoffman also. So these reactions are having similar mechanisms or similar kind of products, and you can use carboxylic acid as a starting material for Curtius reaction. Okay, now let's go ahead and check the advantages of Curtius reaction. So amine synthesis using Curtius reagent is very useful. Range of carboxylic acid groups are tolerated here, like aliphatic, aromatic, heterocyclic, saturated, unsaturated, and lot of. So there is no other reaction like this which tolerates these many groups. So it's very mild reaction conditions we use. So this is again a good advantages and can be done in single pot fashion also. So Curtius rearrangement provides access to primary amine without contamination. This is another advantage, like you will get pure products without impurities. Furthermore, the reaction proceeds with complete retention of stereochemistry of migrating carbon. Means if you start with R stereochemistry, you will get R product. So complete retention of stereochemistry observed in this reaction. So this is very important when you work on peptides or peptide chemistry. So overall this is a very good reaction. So next, moving to how we will prepare acyl azide. So the original way to make azide is using acid chloride. So we'll have carboxylic acid like this, and then we'll treat it with thionyl chloride, so we'll get acyl chloride. Because of this, acyl chloride is highly reactive, so if we treat it with sodium azide, we will get acyl azide, or trimethyl silyl azide, then also we'll get acyl azide. Another way to make azide is we treat acids or esters with hydrazine hydrate, NH2 dot NH2. So hydrazine will treat, then we'll get acyl hydrazines, then nitrous acid treatment will give you acyl azide. So two nitrogens from here and one nitrogen from HNO2, nitrous acid. So you'll get acyl azide like this. So this way we can make azides. Then Curtius rearrangement is conversion of or degradation of acyl azide to isocyanate. So that is our original reaction. Another way of making acyl azide is using DPPA. So if we use dry solvents and DPPA, we'll get acyl azide in very good yields and pure form that can be converted to different products using different nucleophiles. So we'll discuss it afterward. So DPPA is nowadays widely used in synthesis of peptides and Curtius reaction as its workup is easy. Yields are good, but DPPA is toxic and may explode as other azides. So careful or care must be taken to while using DPPA. But if you do workup in water, there is, I think, no problem. So preparation, how can we use DPPA for preparation of protected amines? So Curtius rearrangement, in which isocyanate intermediate is treated or reacted with butanol, provides Bock protected product. Like tertiary butanol we have to use, not simple. So tertiary butanol is like HO, this one, methyl. This is tertiary butanol. CH3 here, CH3 here. So you will get something like Bock protected. This CO gets converted to azide, then azide will react with tertiary butanol to form, this is a nucleophile, to form a Bock protected, this is Bock group protected. This way you will get direct Bock protected from carboxylic. You can do it in one pot also, or you can isolate acyl azide, then treat with butanol or some nucleophile, you will get other product. Same way you can make CBZ protected amines with DPP. Instead of tertiary butanol, you have to use benzyl bromide. Sorry, benzyl alcohol, not benzyl bromide. So benzyl alcohol is portion comes is this function, benzyl alcohol, and then DPPA tolerance. You have to use another solvent, or you can mix them, or in this case you have to use almost 50%, but here you can use 2 to 3 equivalents of benzyl alcohol, then you will get this protected CBZ protected amine. Okay. Then we'll discuss about reaction mechanism. So there are actually there are two types of postulation scheme. Like one says acyl nitrene intermediate and one says concerted mechanism. So previously it was speculated that it goes via nitrene intermediate. The reaction mechanism goes via nitrene intermediate. What was that? Actually, when this acyl azide is heated, the nitrogen gas or N2 gets out, and you will get intermediate like carbene, that is nitrene, so with a lone pair on nitrogen. This when these electron when goes to this carbon, this bond, it gets converted to positively charged. It is getting positively charged. So this, to fulfill the valency, this R group migrates from this carbon to this nitrogen. So that's why it forms a isocyanate intermediate. This isocyanate is very reactive and can be utilized or react with nucleophile, any nucleophile or you can say water, alcohols, amine. So you will get nucleophile addition here, and this UO will go out. Like this you can do. Okay. If you use water, then you will get amine, primary amine. If you use alcohols, then you will get carbamates, and if you use amines, then you will get urea. However, early efforts to trap acyl nitrite intermediate fail. Uh, Previously, it was speculated this form, but when people tried to isolate this nitrate intermediate, they could not isolate this. So then again another mechanism came, like concerted mechanism, where these bonds break at the same time and this R migrates at the same time to form this isocyanate. So this is the latest mechanism, which says concerted, which there is no particular intermediate is formed. So this is again in favor of making stereo or same stereoisomers when we start with the same isomer, and we get same product. So let's check another time the mechanism, like acyl chloride formation, sorry, acyl azide formation. Acyl azide is formed by sodium azide or potassium azide. In this case, potassium azide is shown. So this potassium plus goes out, and you'll get this intermediate, which then converts to acyl azide by the loss of chloride ion. So you will get KCl as a byproduct and acyl azide as product. Then this eventually loses nitrogen. Resonance stabilized, you can write it in this way or in this way. So this way gives when we heat it, this azide, so you will get nitrine intermediate. This is previously a speculated mechanism. So nitrine intermediate is formed, then this R group migrates onto nitrogen, and you will get isocyanate, which can be treated with alcohol to get carbamate, water to get amine, or ammonia or amines to get urea derivatives. So this way you can utilize this reaction to get different products of your choice. So other informations that it can be used or done in presence of Lewis acid or protic acid, but yields are also good without any acid. The reaction uses inert solvent or chloroform if you can isolate, isonate, or aqueous solution to get amines. Directly water workup you do, and you will get amines. Highly reactive acyl azide sometimes not possible to isolate. So now we'll see the synthetic application of this Curtius reactions or Curtius rearrangements. So as I told, the R group can be aliphatic, can be aromatic, or can be heterocycle, this R group. So typical procedure is, like if we try to identify that we have to add DPPA in the base and your SM, so that it will form azide R CO N3 intermediate. First this will form, okay, then this butanol or alcohol will give you protected amines. So in this case we use DPPA, TA, tertiary butanol. Here T-butanol acts as a solvent and as a reagent, solvent as well as reagent. So this is a good reaction because you don't have to worry about many byproducts. This because this is your reagent also and product also, or solvent also. And here you will get only basically azide as a byproduct or as a carboxylic acid byproduct, and this is product. So if you don't have water, you will get, if this is anhydrous reaction, so you will get only Bock protected compound. If it is not, then you can get amine also. So care must be taken while doing this reaction as anhydrous. Another example is, this is an aliphatic carboxylic acid. Here again TPPA, TEAT butanol as a solvent, and you will get Bock protected amine. Here I have shown, I have taken examples of known literature. You can get those from this link given below. So you will get the full paper of this patent of this example. Why I given? Because many people don't know how to do Curtius reaction. So this will give you some idea of doing Curtius reaction. Another example is like 2 carboxyl pyridine. So this one again, if you see here, DPPA, TA and T-butanol, but here the dioxane is added. Why people are adding other solvent? Because sometimes solubility is a matter. So you have to use some solvents which are aprotic and anhydrous. This is very important. So you will get good yields. Here might be possible that they are not use anhydrous solvents. So this byproduct will always be formed, like amines will always form if your reactions are not anhydrous. Okay, so let's go ahead and check another. This is thiazole compound and DPPA, TAT butanol reflux 18 hours, you will get Bock protected compound. So we are discussing about Bock protected compound. Another example like CBZ protected. So instead of butanol, T-butanol, we are using benzyl alcohol here. Okay, so starting material is 7.31, 7.31 equivalent they have taken. And the beauty of reaction is they see this is not very harsh condition because ester is present in this reaction. So it has not been affected here, and yields are also, I think, is good in this reaction. Okay, 1.7 gram, 7.86. Might be using because of this hydrolysis, or sometimes amine you will get. So there are two possibilities only. TA will not break if water is not present. If water is present, then two things can be broken. You can get amine and as well as acid. So that's why yields are less. Another example. So this is very interesting example. So we have got 2 carboxylic acid, this one and this one. So here they are making urea. This is a formation of urea mechanism. This is very important because urea formation is very tricky. You have to be very cautious. So what they did, the first, if you mix them both at the same time, you will get mixture of products. But what they did, they used starting material A first, then toluene, then DPPA to make azide here. Okay, followed by TA, and then mixer stirred for RT for 30 minutes without this B. Then they added B. So azide will form, and this amine, when it comes, it will form urea. Otherwise what will happen? It will form azide here also. So that is a big trouble. Okay. Although some byproducts may form, but they are getting product also in decent yield. So another example, like making of amino acids. Amino acids, how can we make? Like alpha cyanoesters. If we use alpha cyanoesters, then treat hydrazine hydrate as the method of making acyl azide using hydrogen hydrate and nitrous acid, then you can use this acyl azide. So you'll get ethyl carbamate here, and ethyl carbamate can be hydrolyzed to get amines. So this is another example, or very important here to notice is that the stereochemistry will be retained. So that's why it is very useful in peptide synthesis. Some of the one pot reactions been optimized. So this is one pot example to make Bach protected amines, and some of the cyclopropylamines also can be prepared using the same method. And you observe this methoxymethyl ether is not getting reprotected in this reaction. So this is another example where first they hydrolyze this, then use DPPTA dibutanoate cyclohexane to get this Bach protected amine, cyclopropyl amine. Another examples, or many examples are there with this reaction. So azer-methyl synthesis also done. So here is carboxylic acid, then they use DPPATA toluene. So here they use toluene and methanol. See, observe this one. So you will get methyl carbamate instead of terbutyl. Bach group this is not Bach group, this is methyl carbamate. And another thing to observe is Bach is not deprotected, so Bach is there. So this way they made this protected amine, then they cyclized to get azer-methyl. Another is pancreatistatin, which in this reaction what happened, again this is the modified version of Curtius. They used, instead of methanol, they used sodium methoxide, which acts as a base as well and as the another. So this here they got methyl carbamate as byproduct, then they cyclize this. So this reaction, Curtius reaction, is related to a Schmidt reaction, Hoffman rearrangement, Lawson rearrangement. Okay, so this we'll discuss in brief. So here what is in Schmidt, what happens, we use hydrazoic acid, as I mentioned previously, that we use hydrazoic acid, in this reaction. So firstly what we do, we use acid as a catalyst to make this OH group good leaving group, and then we react with hydrazoic acid to get our acyl azide. Acyl azide then gets converted to isocyanate. Isocyanate when reacted with water to get your amine. So this is no need to discuss right now. We'll just discussing similar reactions. So Hoffman is another similar kind of mechanism containing reaction, because another here also the isocyanate forms similar intermediate, but the difference is we use terminal amide in Hoffman reaction, then treat with bromine and NaOH. NaOH, and when we treat terminal amides in presence of NaOH and bromine, it gets converted to isocyanate, which finally converts to primary amine when we do workup with water. So this is another reaction. And finally the Lawson rearrangement, which in which we use hydroxamide as a starting material and make OH is a good leaving group, to using this isocyanate intermediate, which is again reacted with water to get amines. So this way we can get amines from hydroxamides, from free amides, from carboxylic acid using hydroxylic acid, and from carboxylic acid using sodium azide. So this is overall examples and utility of Curtius reactions. So thanks for listening. Have a good day.